Okay, welcome to, this is the first CyberCat seminar, seminar for categorical cybernetics or category theoretic cybernetics. So this talk at least should go on the internet for a general audience, so I'll talk in some generalities. So we are a group of loosely connected researchers interested in applying category theoretic techniques, methodology to questions in control theory, systems theory, artificial intelligence, this kind of thing, things which were historically known as cybernetics, which is a term that has died out mostly, or at least become deeply uncool. But what it seems is that from the category theoretic perspective, several things become very closely connected, which seem to re-bridge this gap and bring these different fields that were historically connected under the umbrella term of cybernetics back together to being related again, which is a kind of odd thing historically. Whether this catches on as a term is a different matter, and partly depends on how successful we are. So in this first seminar, I'm going to talk about lenses, which is a categorical perspective on a certain style of data flow where you have forwards maps and backwards maps interacting in sort of hierarchical feedback loops. And this is a pattern that recurs in many places. Once you start to recognize it, this is a pattern that occurs over and over again. And what I believe is that this pins down something that is folklore to many people. So I think if you told this to many people in many subjects, they would say, yes, I sort of knew this, but writing it down explicitly and carefully and giving it a name seems to be valuable because it builds these bridges between these different fields. So this is what I'm going to talk about today. So I want to really say a little bit about a lot of things, and then I hope that basically for every single thing I'm going to talk about, somebody in some later week will talk about the same thing but in a lot more detail. So I'm going to do my usual thing of knowing a little bit about a lot of things, but not a lot about any one thing. So I think everyone who's on the call knows what a lens is, but I want to make sure that we're all definitely on the same page. So a lens, I guess the title of this seminar is something like lenses as a foundation of cybernetics. Let's write that down. Everyone can see this, right? Okay. So I just want to start by getting us all on the same page, that we all know what lenses are. And because the terminology can be quite confusing, clashing terminology is all over the place in this study of lenses. So I will define a lens for the purposes of this talk. A lens is going to be a pair of functions. So a lens from, Toby, the answer to how I'm doing this is just that I have two different accounts. It's not rocket science. So it's the thing that goes between pairs of sets. So it's just a pair of functions where the first thing goes forwards between the forwards sets, and the backwards thing goes backwards between the backwards sets. So a lens is just, by definition, this pair of functions. So it turns out that if you have a pair of these, xs to yr to zq, and you have a v1 u1 v2 u2, you can compose these sequentially to get a composite lens from xs to zq, where on the top you go from x to y to z just by function composition of the v's, and then along the bottom you had to do some work. So you need to come up with a function from x times q to s, which I'll call u, and the formula for this is u of an x and a q comes from, well, it must be u1 of something. It must be u1 of x with some r. How do we get an r? Well, it's u2 of something. So u2 is something and the q that we have. So we need a y, and the y is going to come from v1 of x. So this formula is like the lens composition law. So the non-obvious fact is that this composition is associative. I don't think this is completely obvious. The hissing in the background just stopped, and it's extremely off-putting because I got used to the noise. Okay, so non-obvious fact, this is associative, so these form a category. We also have an identity morphism from xs to xs, where along the top you're the identity on x, and along the bottom you're the projection x times s to s. And this is the unit of the composition. So it turns out that these form a category. And it's quite an interesting category. It has a lot of very interesting properties, but I don't want to spend too long on this. The minimal setting in which you can define this is a category with finite products. So over a category with finite products, you can make this definition. How do you go to a new page, I wonder? How do you go to a new page? No. Okay, I can just delete it. Okay, please don't ask me to go back because I can't go back now. So there are two different generalizations of this in use. One of these is called optics, and one is called dependent. Well, it goes by several names. Dependent lenses, which are the same thing on the nose as container morphisms, which happen to be isomorphic to polynomial functors. So the right-hand one is kind of obvious. So instead of x, s, and y, r, we now allow s to be a dependent type, and I'm going to do this super informally. So I'm going to write in like pseudo dependent types language. All of this can be made precise by working in a locally Cartesian closed category and being careful. So we allow s to be dependent on x and r to be dependent on y. And then your pair is now v going from x to y, and u, which goes from x to r over v of x to s over x. So this is something like the obvious dependently typed generalization of lenses. If you just let everything be dependent that can be dependent, you get this. This is a super nice category. It has lots of very nice properties. It's equivalent to the category of polynomial endofunctors and natural transformations. So actually, I wrote something false. I said isomorphic to polynomial functors. This is actually polynomial natural transformations between polynomial functors. Nat trans between polyfunctors. Okay. That's dependent lenses. This definition comes up also all over the place. I am told on the authority of David Spivak, basically, that this definition comes up all over algebraic geometry, for example. Okay, the other definition is from, the other generalization is from lenses to optics. So I told you that the minimal setting in which you can define lenses is over a finite product category, but often you want to do this in a category which is just monoidal, but the monoidal product is not a categorical product. Often this happens, for example, because you're working in the closely category of a monad, say a commutative monad. Then you have a monoidal category, which practically always isn't a monoidal, isn't a finite product category. And it turns out that there is a non-obvious generalization of lenses to that setting, which is due to Mitchell-Riley, or well, sort of due to lots of people simultaneously, and it was folklore for a long time. And Mitchell-Riley wrote it down in a clear way, which is called optics, where your objects in your category are still pairs of sets, but now your Hom set from xs to yr is now given by a formula involving a coend, which is something like x2 theta times y times, this is a tensor, theta tensor r to s. So this turns out to be the right generalization of lenses to a monoidal category. If your monoidal product is a categorical product, this turns out to be isomorphic to the old definition of lenses. Okay. The other thing I want to talk about is the int construction, which is a closely related construction to lenses. So instead of having, so a lens is this, ux times r to s. What if you symmetrized this and said that your forwards function can also depend on r? And this gives you the int construction, and you can define this when your category has a trace. So it has essentially a fixed point operator. So this again restricts back to lenses in the case when everything is defined. So this is one of the closely related constructions. I just wanted to mention this because it's something else that comes up in the same sort of setting sometimes. Okay. That much was the getting on the same page part. Is there any questions at this point? Could I have some evidence that everyone's still connected to the call and I'm not talking to myself? Yeah, thank you. It's kind of off-putting.
Here's a question. Is there a monoidal version or other versions of the int constructions the same way you can generalize lenses?
So the int construction is usually given for a trace symmetric monoidal category. The version I wrote happened to be a bit specialized to traced Cartesian monoidal, but that's because I wrote it in a funny way. Yes, and Toby's right that so the category of lenses is not compact closed. It has some weird in-between structure, which I could tell you about, but it will take us in the wrong direction. And the in construction instead is compact closed, so it's super nice. Okay. I want to talk about, okay, so the first application I'm going to talk about is differential calculus, differentiation. Which is the same thing as automatic differentiation. Sometimes my whiteboard pen just stops working. Equals backprop. Yes, thank you. Reverse mode automatic differentiation. So consider the monoid So the monoid of, say, once differentiable functions from R to R. Okay, this is a monoid. So think of this as a category with one object. I can define a functor, which I'll call D, from this monoid to the category of lenses by, so the one object, my one object star is going to be sent to the object R. And then a function, which is going to be a lens from RR to RR, is going to be, so I'm going to call this F sharp, where, so the forwards thing is just F, right? So I just take my function to be the forwards thing. The backwards thing, so what I'm going to do is I'm going to think of elements of the backward sets, the second R in each pair, as an infinitesimal. So I'm going to do a really baby version of differential geometry here. So F sharp, so this is going to be a map from R times R to R, from this R times this R to this R. So it's going to take an X and a thing which I'm going to call dy. So don't be scared by me writing dy. This is technically, so that the technical version of this is it's a vector in the cotangent bundle. But everything is very trivial because I'm in one dimension and everything is flat. So I'm going to define this to be dy divided by f prime of x. And what you should do is you should think of this thing as dx, because then if I rearrange this, I get dy over dx equals f prime of x. So you can now ask the question, is this actually a functor from M to lens? So does this respect function composition? And the answer is yes, and this fact turns out to be exactly the chain rule. So if I take some f from R to R followed by some g from R to R, then if I do d of g after d of f as a lens composite, this is going to be, well, along the top is just function composition, and along the bottom, let's call this h sharp. If I write the lens composition law, oh, that's interesting. That's not supposed to happen. Okay, my keyboard appeared. iPad's palm rejection is not that good. Okay. if I just write the lens composition law, so this takes an x and a dz, this is going to be f sharp of x. I'm just going to mechanically translate this, f of x dz. Expand the definition of G sharp, which is coming from the derivative of G. So this is f sharp of x and dz over G prime of f of x. Now it's starting to look a little bit like the chain rule. And then this is dz over f prime of x, G prime f of x. So if I called this dx and then I rearrange, then I get dz dx is f prime of x, G prime f of x. So this leads me to make the claim that lenses is basically an abstraction of the chain rule. So I sometimes use this slogan now that lens composition is a sort of an axiomatization, sort of an abstracted version of the chain rule. So things that compose by lens composition are essentially composing by a chain rule, not necessarily the chain rule, but a chain rule. Okay. The thing I've just done generalizes to multivariate calculus. You use the Jacobian, which is the matrix of partial derivatives. I wanted to keep things as simple as possible in this talk, so I've done everything in one dimension here. Okay. Next thing I want to talk about is Bayesian inference. This part is joint work and actually mostly done by Toby. Did I spell your name right? Yes. Toby. No, it's an I, not a Y. Sorry. There we go. Okay. Take the category of sets, this is again for simplicity, I'm going to take the simplest possible setting in which I can say the things I want to say. Take the category of sets, take the finite support distribution monad. So d of x equals the set of finite support distributions on x. This is a monad. So this is a baby version of the Giri monad. So the grown-up version of this is on measurable spaces. The Kleisli category of this is the category of it goes by a few names, but finite support Markov kernels. Because so a category from x to d of y, a function from x to d of y is like the same as a function from x times y to 0, 1, satisfying some conditions. So essentially this is a distribution on y conditional on x. And these things composed by essentially matrix multiplication. So if I have a y dependent on x and a z dependent on y, I can associatively compose these conditional distributions. Okay. Now, suppose we have a function f, which is a distribution on y dependent on x. So this is like y given x. And we have a prior distribution on X, and we have an observation of Y, we can ask, so given a distribution on Y dependent on X, everyone's complaining about my infinitesimals. It's fine. This is scaling cotangent vectors by scalars. I believe this is completely fine. Okay, given a distribution on Y dependent on X, a prior distribution on X, and an observation of Y, so just an element, we can ask what is the posterior distribution on X. So given that we have a prior distribution, and then we observed some actual element of Y coming out of this process, what should our updated posterior distribution of X be? So how should we update our beliefs about X? So you can do this by Bayes' law. So and I'm going to call this thing f sharp of pi and y. This is going to be a distribution on X given by, now I've run out of space, so I'm going to go up here. This is a terrible way to do it. So Bayes' law tells you this thing. So it's a distribution on X where the probability that this thing takes on a particular value X is, so this is the probability that pi is X given that f of pi is Y. So by Bayes' law, you can write this as the probability that f of X equals Y times the probability that pi is X divided by the probability that f of pi is Y. And this is all data that you have. So you can just write down this distribution. So I would like to define a map from Kleisli category of D to lens by, so on an object, so an object is just a set. I'm going to take this to the set of distributions. This is a bit of a hack because I'm not sure exactly the best flavor of lenses to formulate this. And then going backwards, on morphisms, this is going to be, so f here is going from X to D of Y. I need a map from dx to dy just because of how I formulated it. So I'm going to take this to be the Kleisli extension of f. So the Kleisli extension in this monad says if you know how a thing depends on pure values, you can just stuff in a random variable and it just works. And then for the backwards thing, I'm going to take the Kleisli extension of f sharp. And it turns out, again, this is not an obvious fact, that B is a functor. So this, again, comes down to some sort of chain law for Bayesian updates. So it says, if you have a sequence of stochastic processes like X to Y to Z, and you have a prior on X and a observation of Z, how do you get a posterior on X? You can do it if you know how to get the posterior for each of these two individual parts. And the way they compose together is by lens composition. Okay. Yeah, Toby has a more refined way of doing this. I've done basically the most naive way of doing this. Okay. I have a few things I want to get through. Okay. Like I said, I want to talk a little bit about a lot of things. The next thing I want to talk about is value iteration. This is joint work with Victor, in the sense that the entire thing is his idea. So the setup here is a Markov decision process. So a Markov decision process says I have a state space Q, and I have an action space A. And then the idea is that I'm in a state and I do an action and then I transition to a new state, and then this thing repeats forever. So you have an agent who is choosing actions in order to move around this state space. And every time they move, they get a little bit of utility, which they want to collect utility over time. And then the question is, how should they optimize this? So formally, we have a transition function. So I'm going to do this. I'm going to do this deterministically, which is actually a very boring setting. You can also do this stochastically. Then you need to use optics rather than lenses. So I'm going to do it deterministically just so I can use lenses to keep things simple. This one really does need to be done non-deterministically to be interesting. So I have a transition function, which given the current state and an action, I get a new state that really ought to be deterministic, but really ought to be stochastic, but I'll pretend it's deterministic. We have a utility function, which says, given a state and an action, we get some utility. And then we have, so this stuff is known. The thing that we want to find is a thing called a policy. So the policy is a choice of an action given what state you're in. So this is sort of the Markov property. It needs to be memoryless. So your action can only depend on your current state. Again, that should be stochastic. In order to maximize, we also need an initial state. Q0 in Q. So a policy determines a sequence of states. A sequence of states, Q0, Q1, which is Q1 comes from the transition of Q0 given the action. Q2 is the transition from Q1 given the action, and so on. And we want to maximize over all stages going to infinity the utility of the current state and the action we do in that state. Except that sum doesn't converge, so we stick in a thing called a discount factor. And discount factor is just a constant which tells you how much you weight utility in the near future versus utility in the far future. So these, at least in the stochastic setting, these can be quite non-trivial things where you need to make trade-offs between getting utility, doing an action that will get you utility now versus doing an action that will get you into a state that will get you utility in the future. So, for example, savings models in economics look like this. Okay, so these things are kind of hard to solve. So Bellman basically introduced problems like this and showed how to solve them. So one of several methods for how to solve them is a method called value iteration. So value iteration is we want to approximate the value of a policy in some state. So I'm going to do a little trick here, because before the initial state Q0 was just a constant part of the data of the problem, but now I'm going to pretend that Q0 is a variable. So I'm going to let Q0 vary. I'm going to imagine myself in different starting states. So I want to approximate this thing. And if I can do this, then I can optimize this thing over sigma. And you can pull a trick where this thing has a self-similarity structure, which is sort of co-recursive, because the value starting in the state 0 looks like the utility we get just from this stage, plus once discounted utility from the next. So this is just a fact about value functions of this form, because I've written this as a geometric progression, so I can sort of re-index by 1. But it turns out that you can solve this functional equation in V by iteration in many cases. Yeah, Victor's correcting me. I'm doing it in this way in order to make it fit into lenses more easily. Again, I'm not certain which is exactly the right way to do this. So normally you talk about the optimal value function, which is this maximized over sigma. You can solve this functional equation in many common settings by picking some initial function for V, for example, V being identically 0, and just iterating this thing. And in common situations, this iteration will converge to a unique fixed point because it's contraction mapping. So, so what you can do, given this data, I can define, so given sigma in particular, I can define a lens, which I'll call lambda sub sigma, from QR to QR. So Q here is my state space, which in the forwards direction, so the V map of this from Q to Q is given by the transition that we do. So F of Q and sigma of Q. And the update, so that takes, so this has type Q times reals to reals. And this is going to be given by, I'm now using U for both update and utility, because I always called the backwards part of a lens U. So sorry, I reused a letter here. Is the utility of the current state plus discounted R. So this real number here is going to be called, this is called the continuation utility. So this represents the utility that we get from all future stages. So this lens sort of handles this re-indexing process. And then it turns out that you can do value iteration using the lens structure so a map from Q to R is the same thing as a lens from QR to 1, 1, because this consists of a map from Q to 1, which is unique, and a map from Q times 1 to R, which is a map from Q to R. So I can take this thing to be my initial guess, which could be, for example, identically 0. And then I'm going to pre-compose this lots of times. And so you can perform value iteration by lens composition, by doing this composition. And I have confirmed in code that this does actually work, and you do get the you do get the right answer. I'm not convinced it's very performant. How do you formalize the lots of times? I don't know. This is a open question. This thing looks sort of limity. Okay. Philip, what time do you think I should stop?
In 5 minutes or so.
Okay. Okay, I want to mention dynamical systems and wiring diagrams because they clearly fit into the cybernetic umbrella, but I don't understand. So no matter how many times I see that stuff, I don't understand it on an intuitive level. So I want to mention that it exists and then entirely leave it for Christina to talk about in a later week. So that's the thing which I've chosen not to talk about. A thing I want to mention is where open games fit into this. So when you abstract a bit, open games have a lot to say about all of these things, and the term open games no longer seems appropriate because you're no longer doing game theory with it. You can do game theory with it, which is something which again fits into the cybernetics framework, which I'm going to choose not to talk about. Lenses is relatively close to, the way that lenses work in game theory is relatively close to this value iteration example. They're neighbors. What an open game is in generality is it's an indexed family of lenses of a fixed type, together with some way of updating or doing some similar operation on the parameters. So most of these examples, you actually want to have parameterized families of these things and then learn the parameters. So in differentiation, you're trying to learn the forwards thing. In Bayesian inference, you're trying to learn the backwards thing because these things are actually integrals, and integrals are hard to compute. So you're actually parameterizing them. Value iteration, everything is parametric here in sigma, and that's the thing that you want to optimize. So all of the examples I've given actually should be formulated in open games, which are essentially lens families plus, so they're lens families plus another thing. And then the other thing tells you how to learn this, potentially how to learn this parameter. So I believe lenses, open games are the natural extension of lenses for many of these problems. I want to very quickly talk about one more thing, which involves unsharing this screen and sharing my laptop screen. So what you're looking at here is joint work with Jerry Swan. This is a very basic control theory example where we have 3 state spaces. So this is about robot control. So I have a state space, which is coordinates, and then 2 abstractions of it. So these are 2 different ways that you can abstract. This is Haskell code, by the way, if you can't read it, but it should be mostly readable-ish. It says that a zone is either zone 1 or zone 2. Double is like real numbers. This thing is product types. So this is a state space and then 2 abstractions of it. And we make a lens. So this is XX to YY. this is XX to YY, sorry. Where in the forwards direction, we do the abstraction. So we say, given where we are in the more concrete state space, say where you are in the more abstract state space. The update thing is like a control, which says, given where you are in the concrete state space and where you would like to be, your goal in the abstract state space, update where you would like to be in the concrete state space. And it turns out that you can sequence these things. So if you an abstraction followed by another abstraction, these things sequence correctly. So you can give it the current state in the concrete state space and the target in the 2 levels abstracted state space. And this thing will, by lens composition, we're calling this thing like semantic backpropagation. This thing will tell you the updated place in the concrete state space. I'm not going to run this because I've actually run out of time. But you can, I mean, this code works. It's nasty because I've done all this geometry code completely by hand. But if you run this thing, we get a robot moving around a map, and I don't have a picture of the map that I'm on the screen that I'm able to share. But you can put the robot as a coordinate and give it a goal in the semantic state space, and then you can watch it moving around. Okay. Yes, that's everything I wanted to say. The punchline is lenses are everywhere in control, optimization, this kind of stuff. This is a potentially a unifying principle across many different fields. My meta belief is that most people would not be surprised when you told them this, that many people feel this in their bones. But we can make it precise. We have the technology to make this precise. Okay, yes, that's the end.
Thanks, Jules. Are there questions or comments?
There's been a lot of chat that I've missed. There's no question. I'm surprised there's no questions because everybody here, every single person here knows more than me about at least one of the things I talked about. That's by design. So everybody should be complaining about something that I did wrong.
I mean, I kind of wanted to discuss a little bit this division in the differentiation thing.
Yeah.
But by the way, thanks for the talk. I learned a lot about pieces that I was vaguely aware of some of these pieces, but that helped clarify some of them to me.
Oh yeah, I should say, I forgot to say, the connection from lenses to backprop was made by Philip Zucker before anybody else, I think.
It's, you know, like all of these things, it's hazy, and like the backprop paper by Spivak was before
everything.
I wrote a blog post, before everything. Yeah.
Everything here is folklore to somebody. That's the problem.
Yeah.
None of this is entirely new. Everything is folklore.
It's true. Yeah, so I just, the division thing just really doesn't set well with me, for the reasons I said in the chat, of that for a constant function, you're gonna have division by 0, which is pretty nasty. And then more importantly, when you go to the multi-dimensional version, now you have Jacobians, you know, like maybe you're going from 2 dimensions to 3 dimensions. So the Jacobian's a 2x3 matrix. And there's no natural, there are inverses you could come up with, but there's no like the inverse of a 2x3 matrix. Mm-hmm. So as I understand it, what the difference between forward mode and reverse mode differentiation is whether you're composing the Jacobian. The forward mode is composing Jacobians as matrices, matrix multiplication. But then reverse mode is composing the transpose of those Jacobians. Okay, so it's not the inverse of the Jacobian, it's the transpose of the Jacobian. And when you take, and if you want, like, they should be giving the same answer. Reverse mode and forward mode are two ways of doing the same thing, just with different performance characteristics. So when you do, if you want to do multiply transposes of matrices instead of matrices, you also flip the order of the whole thing. So that's where you sort of get the backwards action of the lens. And then in 1D, the distinction between transpose and not transpose disappears. So it's sort of not so obvious in the 1D case that that's what you're doing. Yeah, and the way you said cotangent, another way of talking about it in a slightly more mathematical flavor is that you have sort of this vector down here. You have a mapping, a vector down here, and you have a linear function up here, and you want to somehow smash those two together. Well, you can either push forward the vector or you can pull back the linear function. And when you pull back linear functions, you're multiplying by the transpose matrices is how that's done. So
okay. So I would definitely be interested in a talk.
So yeah, I can chime in. I've been thinking about this, and this is sort of part of the paper we're expanding. Part of the paper we're doing on expanding backpropagation functors. So you're completely right, Philip. Yes. So if you have a forward map x to y or Rn to Rm, the backwards map, so the put of a lens, is precisely the Jacobian. And if you work that out, what it is, you can see that's true. So a Jacobian is a matrix, but it also has variables inside, right? Usually it's partial derivatives of the output, right? And so if you work it out, it's precisely the Jacobian. And the reference I would suggest is the reverse derivative categories from I think a lot of Canadian people, and it's really nicely put there. And yeah, you're right. When you go to one-dimensional case, then the Jacobian, basically the difference vanishes, and it's still multiplication, right? So that's sort of the weird part, and you have to be careful here in working these things out. So yeah.
Okay, so yeah, I would like to see a seminar on at least each of the individual things I talked about by somebody that's more knowledgeable than me about each of them, plus each of the things that I didn't talk about.
So I signed up actually on this list for
okay.
December slot, and I'm happy to elaborate on this.
Yeah, maybe a reminder for everyone else who hasn't seen it yet. There is a Google Doc where you can just volunteer to give a talk, and there are still slots available, including the slot in 2 weeks.
Ah, okay. We need a volunteer. Okay. Are there any more questions? This is coming up to the hour, but well. So one thing I didn't talk about is reinforcement learning, which is from my understanding, a relatively small variation of value iteration, or of Markov decision processes from this perspective. So I know Eleanor's been thinking about this and possibly thinks that you can't do this with lenses, or you can't do it with open games.
I think we should close today's session.
Yeah.
And I mean, everyone who still has time can stay in a call a bit longer if he likes to.
Yeah.
And otherwise, we will see how the slots fill up for the next weeks.
Yes, yes. I hope this doesn't fall flat. I hope we do actually get a functioning seminar series that requires speakers. That's the fuel of a seminar series.